I'm Emily.
And I'm Mark.
And for our final project this year, we decided to create an automated bird food delivery system. So the general idea of our project is that it takes in an input via this motion sensor, which triggers a little motor that rotates an auger and delivers food via an auger-style food delivery system.
Alright, so I'm going to go over the components used to make this project. Up first, we have the Basis 3, which houses the Arctic 7 FPGA. This is the board we've been learning to program this quarter. Next, we have this power supply module, which supplies high power that can drive that the stepper can use to drive the auger. Up next is the stepper motor driver, and what this does is it converts the low power digital signals from the FPGA into high power signals that can drive the stepper. Speaking of the stepper, here it is. This is the motor that drives the auger. And finally, we have this PIR sensor in the front. What this does is it senses, through infrared, it senses motion and has circuitry to prime that into a digital signal which the basis can read.
So now to break down the code. Our top level module takes in 4 inputs: the display button, motion sensor, reset button, and clock. And it has 3 outputs: seg and and, which control a display, and stepper, which controls the stepper motor. So the way that this code works is that it takes in an input from the motion sensor here. This input is then entered into the motor delay module, and that module leads to the motor module. The way that the motor module works is that it only rotates if the signal is high, which is given by this trip, and this speed control module right here controls the speed of the motor. Now the rest of this code is involved with keeping track of the number of times food has been dispensed and then displaying that to a 7-segment display. So the motion sensor is an input to this counter module. The counter module increments this counter value by 1 each time this motion sensor is triggered. The counter module then outputs to a universal 7-segment display, which shows the number on this display here. Originally, our code is supposed to take an input called a display button, and every time you push this button, the count is displayed on the display for 10 seconds. This display delay timer right here is what keeps the code onto display for 10 seconds. There is also the reset button input, which goes into the counter, and each time that button is triggered, the count resets to 0.
So here are the clock dividers. These have an input clock and an output divided clock. What this is going to look like is a fast clock on the input and a slow clock on the output. It does this through a synchronous binary parameterizable counter. And it is synchronous because the counter increments at each positive edge of the clock. It is parameterizable with value in, and the amount of times the clock is divided being 2 to the n. It achieves this because the most significant bit of your counter is tied to the output clock divider. Okay, so here's the delay timer finite state machine. These take an input trip, clock, and output delay. The clock is just a regular clock. How this works from the trip and delay input outputs is the trip looks like this, and we want something like this. Essentially, we want to hold on to that short input time. How this works is the finite state machine evaluates if trip is high. If trip is high, then it will also set delay high. Then the finite state machine will go into a continuous counter synchronized with the clock that counts up to a parameterizable counter until it overflows. It checks this by checking the least significant bit and the most significant bit of the counter register to see if it's counted to the top. At that point, it will pull delay low. What that will look like is a trip which pulls it high, the counter starts counting, and then it'll be pulled low when it overflows. This is the stepper motor finite state machine. It has input rotate, clock, and output stepper. The reason we use a finite state machine is because the stepper motor has 4 windings, and this has to be excited in a specific pattern such that this stepper motor can rotate. The reason we have a clock divider is because if we rotated this at every single clock edge, this would occur way too fast at about 100 megahertz. So we have to slow down the clock such that the stepper motor rotates at the right speed. How we accomplish this in the finite state machine is the finite state machine evaluates if rotate is high. If rotate is high, it will go into its sequence of steps to spin the stepper motor, and then it will reevaluate if rotate is high. If this is true, it will keep going in its loop. If rotate is not high, then it will exit and stop driving the stepper motor.
So one of the issues we ran into when designing our code is that the universal 7-segment display code does not behave in a way that allows us to accomplish what we were trying to accomplish. While this display button is supposed to trigger this display to turn on for 10 seconds, and this delay timer is the one that keeps this code projecting onto the display for 10 seconds, we couldn't figure out a way to actually turn off and on the display once it's turned on. And this DPEN input we thought enabled the 7-segment display, but instead it creates just a dot on the display. There isn't actually a way to turn on and off the display in the way that we had wanted it to. Even though this was the case, we still left the display button and the display delay because we had calibrated the rest of our code to match this timer, and it affects what is actually displayed onto the display.
Thank you for watching our video.
We hope you learned something.